we continue with our examples of superposition of different plane potential flows. So, the next example that we will consider is a vortex. Okay. So, when we consider a vortex, remember that we are talking about an irrotational flow and a vortex. So, it is an irrotational vortex or a free vortex. So, what should be its velocity components? We already know v theta equal to c by r and Vr equal to 0, right. So, now this C may be related to the strength of the vortex. Strength of the vortex is its circulation. So, what is the circulation? If you recall, this one, right. So, this is C by R into 2 pi r. If you take a circle of radius r and find out circulation around that. So, C is equal to gamma by 2 pi, where gamma is the strength of the vortex or the circulation. Now, your df dz, that should be Vr minus I v theta into e to the power of minus I theta. Okay. So, minus I c by r e to the power I theta. So, minus I c by z. So, minus I gamma by 2 pi z. So, what is the form of F? F is minus I gamma by 2 pi ln z, right. You have to keep in mind that this gamma we have considered as positive if C is positive, and that is anti-clockwise. So, here this minus sign is for anti-clockwise circulation and plus sign for clockwise circulation, that we have to keep in mind that. So, if gamma is just a number, just a positive number, then this minus sign will imply that it is anti-clockwise and plus sign will mean clockwise. So, if where we are considering gamma as itself a positive number. Now, let us say that we want to simulate flow past a circular cylinder with circulation. So, flow past a circular cylinder without circulation was uniform flow plus doublet. If you want to introduce a circulation, then you have to use this vortex. So, it is uniform flow plus doublet plus vortex. That means, how do you write F? First, for uniform flow, u infinity z plus doublet. For the circular cylinder, flow past a circular cylinder, we have seen doublet strength is special, u infinity into r square, where r is the radius of the cylinder. So, u infinity r square by z plus the vortex minus I gamma by 2 pi. Now, let us see that using this, can we really simulate the flow past a circular cylinder, because you have to remember that the radial location of the cylinder should represent psi equal to 0, the streamline. Let us see whether that is satisfied by this or not. Intuitively that will not be satisfied, because up to this part if we consider that satisfied psi equal to 0 on the radius. Now we have added one extra part. So, how do you ensure that? Let us look into that issue. So, we just write this as u infinity r e to the power I theta plus u infinity by r square by r e to the power minus I theta minus I gamma by 2 pi ln r and plus gamma by 2 pi theta. Right. So, one I with this I square becomes minus 1 and that is how this has become plus. So, if you want to write it in terms of the real and imaginary components, u infinity r cos theta, first let us write the real components, plus u infinity capital R square by r cos theta plus gamma by 2 pi theta. This is the real part. Imaginary part is more important for us because that gives the stream function form. So, plus u infinity r sin theta minus u infinity r square by r sin theta minus gamma by 2 pi ln r. Clearly, if you see, this form does not satisfy the requirement of, one I has to be put here, this form does not satisfy the requirement of psi equal to 0 at small r equal to capital R, right, because when small r equal to capital R, these two terms will cancel out, but the third term will remain, but small r equal to capital R should correspond to psi equal to 0 for flow past a circular cylinder of radius capital R. So, what is the way out? The key here is that this definition of f may always be remain unaltered if you just add, say, a constant p plus iq, right, because it is just the choice of the reference. So, just add p plus iq. So, here you will have one p and here you will have one q. The q should be such that it should be gamma by 2 pi ln of capital R. Then you may, so if q is equal to gamma by 2 pi ln of capital R, then psi equal to 0 at small r equal to capital R. Okay. So, in this way, if you want to generate a body of a particular shape, you have to be very careful about the choice of the f. It is a superposition, but you also may need to add certain constants to make sure that you represent the correct shape of the body. When you have a body of a particular shape, what are the important things of interest? One important thing of interest is the stagnation point. So, where is the stagnation point? For example, when you have flow past a circular cylinder, say without circulation. So, when you have without circulation, this gamma term is not there. So, when you have flow past a circular cylinder without circulation, then you have, when the first term is u infinity. So, if you find out df dz, so df dz if you calculate for flow past a circular cylinder, you got one Vr which is 0 for all r and theta on the cylinder and one V theta which is proportional to sin theta. So, when theta equal to 0, then or maybe r equal to capital R, and but r equal to capital R is okay, but you see the expression of V theta minus 2 u infinity sin theta. So, when theta equal to 0, you have V theta also equal to 0. What about theta equal to 180 degree? Same. So, those points are on the cylinder are special points where you have both Vr and V theta equal to 0. So, those are locations of stagnation points on the cylinder. Stagnation points need not necessarily be located only on the surface of the body, they may also be located at outside. So, the Only important condition that you need to find out is where the resultant velocity is 0, that means Vr V theta individually 0. Okay. So if you consider the flow past a circular cylinder, you will see that if you just want to consider streamlines without the rotational effect or without the vortex effect. So you have a point here which is the location of a stagnation point, then the streamlines follow like this, and this point is also like a sort of stagnation point. So here you see that the theta in the way it is measured classically by polar coordinate positive sign convention, this should be the angle theta, but even here 180 degree minus theta is also fine. So you may also consider by convention this as the angle theta. The reason is that the answer where it comes in the form of sin theta. So it does not really matter, and of course in terms of pressure distribution the sign also is not important, it is just the value, because you have sin square theta coming there, it is like even more inconsequential what is the sign of that trigonometric expression. So by convention we take this as theta, so this is like theta 0 theta 180 degree like that, and you have such shapes of streamlines. Such beautiful shapes of streamlines are not there in the real case, because in the real case when you have adverse pressure gradient at some point close to this one you have boundary layer separation, beyond that you do not have such streamlines, such symmetric shapes. So we will look into that issue more carefully. Now regarding the effect of circulation, let us try to see that what is the effect of net effect of circulation. To understand that, what we will do is we will try to calculate the total lift and drag force on a body. So our next objective is calculation of lift and drag force. Or drag and lift force. In one of our previous lectures we discussed that if you have a plane flow, whatever is the resultant force acting on a body, that if it is resolved into two components, one in the direction of the flow stream, another perpendicular to the direction of the flow stream, the force in the direction of the flow stream is known as the drag force, perpendicular is known as the lift force. So let us say that we have an arbitrary body, let us also consider this as a cylinder but not a circular cylinder. So a very general case of a cylinder, we are not committing ourselves that whether it is circular or whatever shape. Now let us say that this is the free stream direction, and let us try to identify that what are the forces acting on a small element. Let us say this is a small element of length dl. Remember we are talking about only potential flow, not the viscous flow. So on this element what will be the origin of the force? Only pressure distribution. If it is a viscous flow then the shear effect will also come. So you have the pressure distribution. So this is strictly only for potential flow, you have to keep in mind. So this is not a drag and lift force for any general case, for potential flow. Okay. So now this dl you may say that it is as good as traversing dx along x and dy along y, where x and y are these directions. So you may just break it up into two parts, one is like dx along x, another is dy along y. Let us say that the angle made by P with the horizontal is theta, therefore we may say that angle made by dy and dl, that is also theta, right. dl is like tangent to the contour and P is normal to the contour. Okay. Now let us find out that what is the resultant lift and drag force due to P. So you have a P force like P here, you may resolve it into two components. So one is the vertical component, another is the horizontal component, and this angle you have to keep in mind is theta, right. So this is the P direction, we have just separately drawn the sketch for clarity, nothing more than that. So you have a vertical component, you have a horizontal component. So what is the vertical component? P into dl into what? Cos theta or sin theta? What is dl sin theta? Dx. Just look into this triangle of dx, dy and dl. So P into dx. And what is the horizontal component of the force? P into dl into cos theta minus, right, that is minus P dy. So let us call this as, so this is after all on an element, so let us call this as, so this vertical force is nothing but the lift force, because this because the free stream flow is horizontal, so anything perpendicular to that relative to the flow is the lift force, and this is the drag force. Elemental force, so we have represented by differential quantities. Let us now try to find out this complex quantity, again to use the complex calculus dfd minus I dfl. So that is equal to minus P dy minus Ip dx. So minus Ip into dx minus I dy, okay, fine. Dx minus I dy you can just write in a shorthand notation of the complex conjugate of dz, right. Now what is the total force? You have to integrate it over the contour of the body. So why we are evaluating it? See, because if we integrate this in the form of a complex number, its components will give us, the real and imaginary components will give the lift and the drag force together. So if we want to find out the contour integral of so that is nothing but Fd minus IFL, that is equal to the minus I contour integral of P dx minus I dy. Now because it is a potential flow, you may write P infinity plus half rho u infinity square is equal to P plus half rho v square at any point, neglecting the elevation effect. This v square is like what? You can write v square in terms of u plus iv into u minus iv, because v square is nothing but u square plus v square, right. So you have that Fd minus IFL is equal to minus I contour integral, in place of P we will write half rho u plus iv into u minus iv minus P infinity minus half rho u infinity square, this one. Okay. Now what will be the integral contribution of this term? This term is like a constant, right? It would come out of the integral, so it will be contour integral of something into dx plus something into dy. So what is the total dx as you have traversed along the contour? 0. What is the total dy that you have traversed along the contour? 0. So basically what you are doing by evaluating the contour integral is evaluating this integral as you are traversing the contour along a path, particular direction. So this integral of this term will become 0. Next let us try to look into say the form u plus iv into dx minus I dy, because that is one part of the integrand that you have to evaluate, u plus iv into dx minus I dy. So you can write it as u dx plus minus I u dy v dy, right. Now what can you say about this term? The contour of the body itself is a streamline, so you have dx by u equal to dy by v. So this term will be 0 on the contour of the body. So this is 0 because contour of the body is a streamline. Similarly you can show that this will become nothing but u minus iv into dx plus I dy, just the conjugate terms, because there in place of this minus I you will have just a plus I, and since this term is 0 it does not matter. Okay. So what you are left with? You are left with the expression in place of u plus iv into dx minus I dy, you can write u minus iv into dx plus I dy. So fd minus ifl is equal to minus I, the contour integral of half rho u minus iv, in place of u plus iv into dz star we can write this will not be there. Okay. So okay, it will go to the other side, right. So this will become plus. Okay. So u minus iv into dz, right. In place of u plus iv into dz star we have written u minus iv into dz, this is dz. What is the advantage of this? You see what is u minus iv, this is df dz, right. So we can write this as I okay. So what is the advantage of this? If you know what is the complex potential capital A for the superposition of flow, you may just use this simple integration, equate its real and imaginary components to get the lift force and the drag force. This is known as Blasius force theorem. So it is as good as evaluation of an integral of the form, so half I rho into some function of z dz, where the function of z is df dz square, right. This is the form, mathematical form. Now let us look into this mathematical form for flow past a circular cylinder with a circulation. Before that we will try to understand one important thing, that how to evaluate these integrals. There is a very simple way in complex integration known as residue theorem, by which you may very simply evaluate such complex integrations. How it is possible? Let us say that you have a function fz which has a singularity at z equal to a, okay. So this you may expand in the form of a series, like you will have some negative powers and some positive powers. So let us say you have okay. So it is just like an extended form of a Taylor series where you also have the possibilities of incorporating the negative indices. This is known as Laurent series. So what is known is that integral of f z dz is nothing but 2 pi I into the sum of residues at points of singularity in the domain. To understand that carefully, let us assume that, or just as an example, let us assume that a equal to 0 as an example. A equal to 0 means z equal to 0 is a point of singularity, like if you have a form of 1 by z or 1 by z square, right. So that has a point of singularity. Now the question is that when you have that as a point of singularity, how do you handle that? So let us say that you want to evaluate an integral of, see when you have a equal to 0, that means you are having to deal with integrals of the form 1 by z square, like that. Let us just look into one such form. Let us say you are interested to evaluate the integral of dz by z square, because integral of the function evaluation is as good as like integral of evaluation of the integrals of the corresponding terms, term by term. So if you do that, so let us say z is equal to r e to the power I theta. So we may convert it from z to r theta system. So what is dz? I r e to the power I theta d theta. So this will become, so contour integral of this I r e to the power I theta d theta by e to the power 2 I theta. By r square, right. So what will be this? So now the basis of this is changed from theta equal to 0 to theta equal to 2 pi, okay. So if you see now, forget about the one, forget about the I r square, those contributions, you will get a basic form e to the power minus I theta d theta. So cos theta and sin theta both integrated from 0 to 2 pi. So what will that give? That will give 0, right. So this will be 0. Similarly the higher powers of z will do the same, but if you just consider integral of dz by z, then you will have I r by, now in place of z, r e to the power I theta, so I r by r integral d theta 0 to 2 pi, right. So that is 2 pi I. That means the key is this term. All other terms of that type 1 by g square or whatever, those terms do not contribute to the integration, and the residue is nothing but its coefficient. So C minus 1. So it is as good as, so if you have just one point of singularity, this residue is C with subscript minus 1. If you have many such points of singularity, just it will be sum of such coefficients. So it is very straightforward actually, I mean it is not a very complicated theorem, but a very convenient and powerful theorem. So now for our special case of flow past a circular cylinder with rotation or with circulation, we have to just evaluate what is df dz and what is the coefficient of 1 by z in that. That should be good enough for us to evaluate this integral. So let us do that. So for that flow you have f z is equal to u infinity z plus u infinity r square by z plus or minus I gamma by 2 pi ln z. Let us consider that we are assuming a clockwise circulation. So if we assume a clockwise circulation, we just put a plus sign here with an understanding that we are assuming a clockwise circulation. So the circulation is clockwise, plus you have that p plus iq whatever. What is important for us is df dz, that is u infinity plus minus u infinity r square by z square plus I gamma by 2 pi 1 by z, right. What is our matter of evaluation? That in the square of this one, what is the coefficient of 1 by z, right. That is the integration that we have to do for the Blasius force theorem. So what will be the coefficient? So it is just like a plus b plus c whole square. So the corresponding coefficient will come only when you have these 2 AC, that term. So what will be that? 2 u infinity I gamma by 2 pi, right. So this will become I rho by 2 into just 2 u infinity I gamma by 2 pi, okay, into there is a 2 pi, right, 2 pi I. By the residue theorem it is 2 pi I into the residue, right. So what are the terms that get cancelled out? One is this 2 pi get cancelled out, this 2 gets cancelled out. So you have this as minus rho u infinity gamma I, because I square is minus 1, so 1 I remains. So this is Fd minus IFL. So what is the drag force? 0. What is the lift force? Rho u infinity gamma. So the drag force equal to 0 was thought of as a paradox for a long time, because if you have a say circular cylinder or cylinder of any shape immersed in a flow, when the fluid is flowing on the top of it, there is some drag force that is experimentally calculated. But when this was evaluated theoretically, then it gave rise to a 0, and this was a paradox for apparent paradox for a long time, and it was called as a D'Alembert's paradox. The whole idea of this paradox is, this is not at all a paradox, it was a paradox only at that time, and the reason is that this neglected the effect of boundary layer. So it just considered a drag force with pure potential flow based calculation, where viscous effects were neglected altogether. But although the Reynolds number may be large, but there is always a very thin layer called the boundary layer, within which the viscous effect is very, very important. So we cannot disregard that and calculate the drag force. So that was the whole origin of this apparent paradox. But this lift force was something which which was found to be quite accurate even later on, and one of the important consequences or conclusions of this is you see that in the lift force expression, of course these are forces per unit length perpendicular to the plane of the figure, that you have to keep in mind. This force is apparently not having anything in the expression which is a function of the shape of the body. So this type of lift force expression is not just valid for a circular cylinder, although we established this case through an example of a circular cylinder, but even for bodies of other shapes. And one of the interesting shapes for which the flow induced lift force is very, very important is the aerofoil shape, and even for an aerofoil shape this similar expression for the lift force is valid, and this is therefore known as a very important theorem or very important expression in aerodynamics known as Kutta-Zhukovsky theorem.